Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to everyone. It's an honor to introduce our speaker today, Associate Professor Mohammed Parvez Anwar from the University of Nottingham Malaysia. Okay, just a little bit about himself. He is an expert in structural engineering with extensive research in vibration control, wind-induced response in structures, and sustainable materials. Okay, Dr. Parvez holds a Doctor of Engineering from Yokohama National University, Japan, where he focused on adaptive control of wind-induced vibration in suspension bridges. He also obtained his master's degree from the National University of Singapore and his bachelor's in civil engineering from Bangladesh University of Engineering and Technology. With over 15 years of academic and research experience, Dr. Parvez has contributed to numerous international publications and serves as a reviewer for a high impact engineering journals. He has also been involved in multiple industrial collaborations and research projects related to advanced construction material and structural performance. Today, we will share his insight on the vibration engineering, which is a crucial aspect in civil and structural engineering. So let us give a warm welcome to Associate Professor Mohammed Parvez Anwar. Okay, okay, everyone. I'll be clapping on behalf of everyone.
Thank you
Okay,
very much. Thank you
all
very
right,
much
Dr.
for asking.
Parvez,
Yeah, it's my
it's all
pleasure.
yours.
Yeah. Okay. Thank
Okay.
you. Assalamu alaikum and a very good morning. So I'll start my presentation and then I'm gonna turn off the camera to save some bandwidth. Okay. All right. Okay. Can you see the screen?
Yes, we can.
Okay. So vibration or dynamics in civil engineering. So I think you have already learned about the static analysis in structural mechanics. So if you do not know the vibration or dynamic analysis, you're going to miss a lot of things because I'll let you know what happens, right? In there. So in this lecture, we are only going to learn about the single degree of freedom system subjected to free vibration because it's only 1 hour. I cannot cover too much in 1 hour, right? So in static analysis, you have already seen that the loads acting on the structure, it doesn't vary with time. It doesn't change with time. It's fixed. So no matter whether it's a beam or it's a portal frame or a 3-story, 4-story building frame, in static analysis, the loads acting on it will be a constant load. Either it can be lateral loads, it can be vertical loads, or any other forms of loads, say about dead load or live load. It will be a fixed load. It's not going to vary with time. But when we talk about dynamic analysis, vibration-induced loads, then the load varies with time. And then a few very common types of loads in dynamic analysis in civil engineering are the wind load, wave load, and seismic or earthquake loading. And then since the load varies with time in dynamic analysis, the responses will also vary with time. Now, it may not be the same displacement as you are going to get in static analysis. This displacement may be enhanced several times, sometimes 20 times, 50 times. So that will eventually increase the internal forces dramatically. So if you don't consider dynamics in your analysis, you are going to underestimate many of the loads if you're considering the wind, wave, or seismic loads. Okay, so what are the dynamic loads then? Any set of load or any kind of load that varies with time, that is not fixed over time. So there are two types of dynamic loads that we usually encounter in structural dynamics. One is a random load. Random load is a load that you cannot forecast or you cannot predict. For example, wind load. If you look at the wind variation on a certain time of a day, you will see it varies with time dramatically. Okay, sometimes it may be zero, sometimes it may be very high, and then another issue with wind load is it will also change the direction. In one instant, maybe it is flowing from the west. In next time, it will be flowing from the south or southwest, and so on. So it does not only vary with time, it also varies with in terms of direction. And then another very common random loading is the seismic load. The bottom figure here shows you the acceleration induced by an earthquake. So since this acceleration somehow will be translated in the structure in forms of load, because you know from Newton's second law that F equals to ma. So if the structure is subjected to any kind of acceleration, it will feel a force, right? So you can see it's a very random type of vibration that will be induced by earthquake or seismic load. So in these cases, you cannot actually predict. These are given by God. These are given by Allah. So you cannot predict that how it will vary with time, right? So that's why this is random loads. The second type of load is deterministic load. So it can be a man-made load or created by ourselves. So this load can be of two types. One is periodic, and then another will be non-periodic.
Dr. Parvez, I'm
Right.
sorry
So
to interrupt. Is your slide supposed to be
yes,
moving?
yeah, I'm
Is yours?
showing the deterministic loads now. Is it fixed in the first slide?
Oh, it's still at the first slide. Okay,
Okay.
now it's changed. Now it's changed. Okay.
Okay. Okay. Can you see the deterministic load now?
Yes, I can.
Okay. 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 Maybe if I use the slideshow, it's not changing. So I'll use this type. All right. No problem.
All right.
Okay. So when I talk, okay, maybe you didn't see the. Okay. So the top figure here shows you the wind speed variation. And then somehow in your wind engineering, you will see that wind speed can be translated to the wind load acting on the structure. So if the wind speed varies with time, so will the load acting on the structure. And then this figure is showing you the seismic loading in terms of acceleration. You can also see that it's a very random type of load. Okay, so the acceleration varies with time very randomly, and then therefore the loads created by this, if you are studying earthquake engineering, you'll know how you can calculate the loads acting on a structure from the acceleration created by the earthquake. All right, the second type is the deterministic load. The deterministic load can be of two types. One is periodic loading, the other is non-periodic loading. For example, the figures here shows you 1, 2, 3, 4, 5, 6 graphs of periodic loading. So you can see the same type of load is repeated. Okay, it's repeating. That's why it's periodic loading. So if you just take one sine wave, that will be non-periodic load. Can anyone tell me what is the last figure showing here? The one at the right bottom. Is it a random loading? It looks like a random loading, but this is not. It's actually combination of the other 5 sine waves with different frequencies. All right, so you can see if you know about the Fourier transform, you will know that any random load or any random signal can be decomposed into infinite numbers of sine waves. So this is actually the other way around. If you sum up infinite numbers of sine waves, you will see it will form like a random type of loading. Okay, so if you add these 5 sine waves, you will get this, the last one. So this actually, it looks like a random load, but this is also a periodic load. And then this type of deterministic load can be created by us human beings. For example, if you put a motor on the floor of a building, then it will create some harmonic loading. If it runs at a certain frequency, it will create some form of harmonic loading on the slab itself, and then that will be translated to the beams and to the foundation somehow, right? So this is actually man-made or created by us, the deterministic load. Okay, a very common term used in structural dynamics, the basic is single degree of freedom system. Now, when we talk about degrees of freedom, it's very simple. How many ways the structure can actually deform, how many ways it has the freedom to deform. So single degree of freedom system, when you talk about it, it has only 1 degree of freedom. And then in terms of mathematics, if you go to the deeper in engineering terms, you will have only 1 equation to express the system. So the number of degrees of freedom is actually the number of equations needed to describe the response of the system. And then if you talk about the layman's term, the number of degrees of freedom is the number of ways you can deform a structure or deform a body. And so when we talk about the single degree of freedom system, it has only one degree of freedom. So it can be described by 1 equation. Example, We can have the single-story building, overhead water reservoirs, or observation towers, observation decks, for example, the KL tower or any airport control towers. Okay, so where all the masses can be assumed to be concentrated at a certain point. If you think about observation towers, for example, KL tower, you can see there's a huge mass that is concentrated at the top, connected by a long column, right? So this kind of structure can be idealized as single equilibrium system. So this is okay. Can you see the slide now? There's some animation here. Oh, okay, thank you. So you can see here, if you just compare, let's say any airport tower or the KL tower, you see the mass, the most of the mass is concentrated at the top, which is connected by a column that is fixed at the bottom. Okay, so the single equilibrium system here has a mass M. Now, all the masses, if you calculate of the superstructure, the part that is at the top, then it will be the mass of the structure. And then the column will have two properties. One is stiffness, the other is damping. Can anyone tell me what is stiffness? Don't be shy, just tell me. Anyone tell me? Okay, stiffness, yeah. Anyone?
Stiffness is like rigid, doesn't move.
Yes, stiffness somehow is related to the displacement. So if you apply a force, how much the body will deform, it will depend on the property that is known as stiffness. Okay, so if I show you here, stiffness determines how much the structure will deform under a given load. You think about maybe 1 meter rod. One is made of steel, another is made of rubber, another is made of wood. If you apply the same load holding one end of the rod, and if you apply the same load on the other end, you will see for the same load, the different material will deform differently. So that means there is a certain property that is preventing it from deformation. So that is the stiffness. And then the damping is another property. There's a very important property in structural dynamics that will determine how fast or how slow the structure will come back to its equilibrium position if you displace it from its equilibrium position. So say, for example, the mass is somehow displaced to the right by 1 meter. And then if I let go, how fast or how slow or how will be the behavior, that will be depending on the damping. So damping is represented by C. Now, damping is a very complex property of the structure. It will depend on the internal friction between all the materials of a structure. Say, for example, if you think about the column of the KL tower, is very difficult to actually calculate the actual damping of the system because that is made of so many types of material. It has concrete, it has steel, it may have some other forms of material as the finishing and so on. So it's really very difficult. So we have to have some mechanism to calculate the damping of the structure. And then since we're talking about dynamics, therefore the load will vary with time. You can see here P, and then there is a parenthesis T. So the load is varying with time. At any time, the load may be 0, and then one instant it may be like 1 kilonewton, 2 kilonewton, 3 kilonewton, and then another instance it may be negative 1 kilonewton. So it will be acting in the other direction. So if you look at the arrow here, it's pointing to the right, right? So at some point, this load may be pointing to the right, so to the left. So it will change the direction as well. So since the load varies with time, the deflection is very commonly vary with time, right? So that's why there is a T here in the parenthesis, UT. So the displacement will also vary with time. Now, let us idealize this single degree of freedom system, or let's say this is our KL tower, by the spring mass damper system. So if I idealize this, it will look something like this. Now, do you agree with me that I am representing the left-hand side, my KL tower, with the left-hand side figure here? You see the mass, if you look at the right-hand side, the mass can move in the horizontal direction. So I'm putting some wheels at the bottom, frictionless wheel, so that it can move. You see, the mass can move to the right or left, whatever direction, depending on the force. And then the load applied is here. Now the stiffness is represented by a spring, and the damping here is represented by a dashpot. If you look at this figure, I don't know whether you can see it, the figure with the damping. See, this is a dashpot. What does it look like? Can anyone tell me? You see, this is actually a pot. This is actually a pot or bucket. It will be filled with a viscous fluid, and then this one, the horizontal line, and the end, there's a vertical line. This represents, for example, if you put a circular plate at the end of a rod, and then you put it in the bucket filled with, let's say, for example, oil, and then if you try to move it vertically up and down, then something will prevent it from motion, right? That is the damping. So depending on how viscous your fluid is, say, for example, if you put water in the bucket and then you try to move it in a velocity, certain velocity, probably it will be very easy to move. But if you put, let's say, for example, cooking oil or some other form of oil with very high viscosity, then you will be having difficulty moving it. So that part, the dashpot, will actually represent how fast or how slow the structure, if it is deformed, will come back to its equilibrium position. You see, because of the spring, it will always try to come back to its equilibrium or static position. And then how fast or how slow, that will be determined by the damping or the dashpot. Now, as civil engineers, we have to find the internal forces. So we have to draw the free body diagram of any system. Now, free body diagram is a certain part of the structure that you have to cut, separate with all the internal and external forces shown on the structure. So if I draw the free body diagram, so if I just cut it somewhere in the middle of the spring and the dashpot somewhere, so that will give me two internal forces. The top one will give me the spring force, and then the bottom one will give me the damping force. That's why the subscripts are S and D. Now, you see, since the load varies with time, the PT varies with time, these two internal forces, the spring force and the damping force, these two forces will also vary with time. That's why there is a T in the parenthesis. All right? Now, let us quantify.
Sorry, doctor.
Yes, is it stuck in?
Your slide's still not moving.
Can you see now?
Yes, yes.
Okay, all right. So this is the spring mass damper system. And then if I cut somewhere here, then you will see the free body diagram. So the two internal forces. So one internal forces will be governed by the spring, that is the spring force, FST. And then another one will be the damping force, FDT. The T in the parentheses represent the time variation with, since the load is also varying with time. So if we want to see the three forces acting on the system here, the external force PT that we are applying, and then the internal forces that will be developed because of the movement. One is the spring force, the other one is the damping force. Now, since this system is not in static equilibrium, we cannot apply the three equations of static equilibrium, which are sum of all the forces in one direction equals to 0, sum of all the forces in the perpendicular direction equals to 0, and then sum of moment about any point equals to 0. Now, these three equilibrium equations are only valid for a body that is not moving, that is static. Now, since the body is moving, we have to apply Newton's second law to get the equation of motion. Now, before that, let us quantify the stiffness and damping forces. The stiffness force is always related to the displacement, as you can see here, ut. And then the damping force will depend on the velocity. So the velocity is nothing but the first derivative of deflection with time. You can see ut is the displacement. So if I differentiate ut with respect to time, du over dt, that will give me the velocity. Now in structural dynamics, we don't want to write so many symbols. So that's why du by dt, that is represented by u dot. You can see there's a dot on top of ut. So whenever you see a single dot, that means this is the first derivative with respect to time. In this case, u dot is the velocity. So if I differentiate again, if it is d squared u by dt squared, then there will be two dots that will represent the acceleration. So that will be u double dot t. So the stiffness force is always related to the deflection, and then the stiffness coefficient k. Similarly, the damping force will depend on the velocity. So how fast or how slow you are trying to move the structure. The faster you try to move, the higher will be the damping force. The slower you try to move, the lower will be the damping force, and so on. And then this is represented by the property of the structure, that is C, damping coefficient. And if you apply the Newton's second law, force equals to mass times acceleration, you have to use the resultant force. Now, if we assume the right-hand side to be positive, you can see the resultant force will be Pt acting to the right minus Fs acting to the left minus Ft acting to the left. And then if we substitute Fs and Ft that we have in the left-hand side equation here, and then the right-hand side will be mass into acceleration. The system had a mass m, and then acceleration is the second derivative of u. So that is u double dot t. Now, if I rearrange the equation, sending the external load to the right-hand side and putting all the internal forces and inertia force to the left-hand side, that this will be my equation of motion. All right. If you go to the next slide, you will see the equation of motion. Now, this equation of motion can be explained, such a long sentence. So this is actually the equation of motion of a single degree of freedom system that has a mass m, damping coefficient c, stiffness k, and which is subjected to a time varying load pt, and then that is undergoing a time varying deflection of ut. All right. You see, when you want to explain the equation, you have to explain all the terms. Of course, u dot t is the velocity and u double dot t is the acceleration. Those are the first and second derivatives of ut. So you don't have to explain those things. All right. So now if we solve this equation for different situations, then we will know the solution, how the system will behave. Now, in this particular lecture, we are only going to talk about the free vibration. Now, free vibration, when we talk about free vibration, we'll consider two cases. One is undamped free vibration, and there will be damped free vibration. Now, undamped free vibration is an imaginary thing. We use this to find a certain property of the structure. There cannot be any structure without damping. So you want to use this assumption that the system doesn't have any damping, and then we try to find certain property of the structure. Okay, so when we talk about undamped, that means there is no damping. So the term C is equals to 0. And then when we talk about free vibration, that means the structure will vibrate freely. That means there will be no external force. So PT will be 0, C will be 0. Then if these two are gone, you can see the spring mass damper system will be represented by these. So if there is free vibration, there is no external load, how the structure will vibrate? There is no force. So how this structure is going to vibrate? You have to give some initial condition. For example, yes, please. Can you tell? Yeah. Hello. Yeah, so the structure will vibrate without any external load if we give some initial condition. For example, if I displace the KL tower by pulling it with a very high capacity crane and then let go, then it will vibrate, right? Or somehow if I hit the top of the KL tower by something with a certain velocity, then it will vibrate, right? Or the combination of these two. So you can see here u0. So I have to give some initial displacement, or u dot 0 initial velocity, or the combination of these two to have my vibration of the structure. So if I displace my structure from the equilibrium position and then let go, that is my initial displacement. Or if I hit the structure in a certain velocity, then it will vibrate. Or it can be a combination of these two. I displace it by pulling the KL tower, and then by maybe hitting it with a certain velocity, and then let it go. So it will vibrate with a certain. Okay, so there is no external force, and then there is no damping of the system. So if you look at the equation, the C term and the P term are actually gone. Okay, let me go to the. Yeah. Can you see the slide and the animations? If I go to the next equation, is it still at the previous one?
Yes, we still at the free vibration undamped SDOF system. Page number 2.
Is it 2, right? Is it showing the 2?
Yes, exactly.
Yeah. Okay, all right. So you can see here the equation of motion was, there was 3 terms to the left-hand side and there was 1 term to the right-hand side, right? So the right-hand side was PT, and the left-hand side, the C term is gone. So therefore, the equation of motion is something like this: mu double dot plus ku equals to 0. Now, this is the second order homogeneous ordinary differential equation, because the right-hand side is 0, and then it contains a second derivative of u. That's why this is a second order homogeneous ordinary differential equation. And if you have learned about the solution of ordinary differential equation, you will know that this kind of equation will have a solution in the form of this: u equals to a constant a multiplied by e to the power lambda t. Okay, lambda is another constant. So here a and lambda are the 2 constants which we have to determine based on whatever situation. Now, how can you get a and lambda? I have to substitute this u in the equation of motion. So if I differentiate u with respect to time once, I'll get u dot. If I differentiate again, I'll get u double dot. So this one can be substituted in the first term in the equation, and then u can be substituted in the second term of the equation. And if you do that, you can see here, this will be the governing equation. And then if you take the common term a to the power lambda t, it will give you this equation. Now, this is the product of 2 terms equals to 0. So either of the terms will be 0. Since I have assumed the solution of the equation is to be a e to the power lambda t, so this one cannot be 0. Therefore, the other part will be 0, right? M lambda square plus k equals to 0. So from here, I can get my value of lambda. Since I'm square rooting it, there will be 2 roots, plus minus. And since there is a -1 inside the square root, there will be a j. I know you have learned about the imaginary number square root of -1 as I in your mathematics, but in engineering, we usually try to put it as a j. So I and j actually are the same. It's a complex number, square root of -1. Okay, so if you can see here, we have 2 roots, 1 positive root and 1 negative root. And if you know about the solution of ordinary differential equations, if the equation has multiple solutions, the final solution or the complete solution will be sum of all the possible solutions. So since here I have 2 values of lambda 1 and lambda 2, my solution will be a1 e to the power lambda 1t, a2 e to the power lambda 2t. And we already know what is lambda 1 and what is lambda 2. So if I substitute here, I'll get this. A1 and A2 are another 2 constants. We'll try to determine this later, slowly, all right? So this is our equation. This is our solution now. A1 e to the power something plus A2 e to the power something times t. Now, if we convert the exponential terms into trigonometric terms by these 2 identities, do we know what is an identity? Anyone? What is the difference between equation and identity?
Please explain.
Okay, identity is something that, you see here, the left-hand side is something, right? E to the power j theta, and then right-hand side is cosine theta plus j sine theta. You cannot actually say that this value and this value are equal. An identity is something that will represent, for example, if I expand e to the power j theta in Taylor series expansion, that will be equal if we expand cosine theta in Taylor series and add it with j times Taylor series expansion of j sine theta, then the left-hand side will be equal to right-hand side. So that is an identity. That is not an equation. So somehow the left-hand side, if you expand it in Taylor series, it will be equal if you do the same thing, cosine theta plus j sine theta, this identity, this two terms in terms of Taylor series. So these two will be equal. Simply speaking, let's say cosine theta, if I expand, is in Taylor series. I'm just simply telling it. So let's say cosine theta is 1 plus 3 plus 5 plus 7 and dot 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 so on. And then if I expand j sine theta, it will be 2 plus 4 plus 6 plus 8 and so on until infinite. And then if I expand e to the power j theta, it will be 1 plus 2 plus 3 plus 4 plus until infinite. So that's what it means. So if I add this cosine and j sine theta in Taylor series, it will add up to be e to the power j theta. So using these two identities, e to the power j theta and e to the power minus j theta, we can convert them into trigonometric terms in terms of cosine and sine. Okay, so if I do that, you see the positive j theta will give me cosine theta plus j sine theta. The negative j theta will be cosine theta minus j sine theta. So if I use these two identities in case of these two terms here, I'll get an expansion like this. And you can see here there are two common terms, cosine, and then there will be sine and sine. So if you bring them together, you will see the equation will look something like this. And again, you see a1 plus a2, these are constants, and then j times a1 minus a2, this is also a constant. So therefore, I can replace these two with simpler constant, let's say c and d. So that's why the equation is looking like this now. The term inside the bracket, inside the parenthesis, square root of k over m will represent a very important property of the structure, that is frequency. Frequency of vibration. Can anyone tell me what is frequency of vibration? What is frequency? What does the term frequency mean? Vibration frequency. Yes.
Okay, anyone can answer? The Parvez answer. If not, I will answer. Well, frequency
Yes,
of
please,
vibration is considered, is actually referring to the number of oscillations or cycles per unit.
Yes, per unit time, right? So how many times?
Per
Say, for
unit.
example, you are talking, we are thinking about the KL tower. So if I displace the KL tower from its equilibrium position by, let's say, 10 meter and then let go, how many times it will vibrate in 1 second? That is the frequency in hertz. So let's say the frequency is 10 hertz. That means it will vibrate 10 times in 1 second. Now here, the one you see here, omega n, is actually the angular frequency. Angular frequency is in radian per second. And there's a relation between angular frequency and the frequency in hertz. If you multiply the frequency in hertz by 2 pi, you will get the angular frequency.
So
Right?
is there actually a allowable limit for the frequency value? What I mean is the higher the better, or actually the lower the better? Can you explain that to the students?
Okay, the frequency
For a
actually,
building,
it depends.
for a building,
Yeah,
for a
you can see
building or
here
for
the
bridges, it's different, right?
Yes, of course, yeah. You can see here the frequency is always dependent on the K and M, the stiffness and mass of the structure. Now, say, for example, you have a frequency of your structure 10 hertz, okay? And then if you apply a load that also has a frequency very close to 10 hertz, so these two may resonate. So this frequency, if the applied load frequency and the structural frequency are the same, then the structure will vibrate with very high amplitude. That's why we always try, this phenomenon is known as resonance. That's why we will always try to avoid this kind of phenomena where if you know the load frequency, for example, let's say you are putting a motor on the floor slab that will create a frequency of 100 hertz. Now, I will obviously not design my floor slab so that it will have its frequency near to 100 hertz. I'll either make it like 10 hertz or we'll try to make it very high frequency, let's say 500 hertz, which is far away from the frequency of the applied load to avoid the resonance. Resonance is when the frequency of the applied load becomes very close to the frequency of the structure itself. Then there will be very high amplitude vibration. Okay, you can see here, you can play around with the stiffness or the mass to change the frequency. So if you know the applied load frequency, you can always play around with the stiffness or the mass of your system to change the structural frequency. All right, so you can see here, I have replaced square root of k over m by omega n, which is the angular natural frequency. Now you see it's natural frequency. That means if the structure is displaced from its equilibrium position and let go, it will vibrate naturally at that particular frequency. So you see here, now the equation is very simple. It looks something like this, right? So you can see here is a summation of cosine term and sine term with C and D. Now C and D are the amplitudes, right? If you look at the sine equation, omega n is representing the frequency, D is representing the amplitude. Similarly, if you look at the cosine term, omega n is representing the frequency, C is the amplitude. So if I plot cosine, C cosine omega t separately, if I plot D sine omega n t separately, both will be harmonic motions, right? And then if you add them together, finally, it will also be a harmonic oscillation. So it will give me a sinusoidal oscillation with some phase angle. Now, how to get C and D? C and D can be obtained from the initial conditions. How much you displaced your structure or how much velocity you have given to the structure in the beginning. Okay, now this equation can also be simplified using some trigonometric modifications like this. So this can also be written as this equation. E sine omega nt plus theta. So this is, you can see, this is a sinusoidal curve with a certain phase angle theta. So when you plot this one, this equation, and when you plot this equation, these two will actually give me the same plot. E will give me the amplitude, the total amplitude of the vibration, which is actually square root of c square plus c square. And then if you convert theta from this equation, you can calculate theta. This will give me the phase angle. Okay, so you can see here how you can change the frequency of the structure. If you increase the stiffness, if you increase the stiffness K, obviously the frequency will increase. And you can see here, frequency and period are actually reciprocal to each other. You see, frequency, 1 over frequency is actually the period. The period is how long it will take to complete a full cycle of vibration. Let's say, for example, I displace my KL tower by 10 meter and then let go. So the moment I let go, it will go to the other side and then come back to that position where I displaced it. So this time taken for one full cycle is the period of vibration, T. And period of vibration is nothing but 1 over the frequency in hertz, which is actually omega n over 2 pi. So Fn is omega n over 2 pi. So these are the two equations. So if you want to reduce the frequency of the structure, what do? You increase the mass. You make it heavier. You just imagine you put an eraser at the end of your ruler, and then you try to displace it and then let go. It will vibrate, right? The bigger the ruler, the lower will be the frequency. So the bigger the eraser you put, the higher the mass, the slower will be the frequency. So it will move with a lower frequency and so on. Okay. And then if we use the initial conditions, for example, if I use the initial displacement as 0.5 meter and then initial velocity 0.8 meter per second, we can actually calculate the values of C and D. How? I have to put this displacement and this velocity in this equation to get C and D, Because I have two unknowns, I'll need two equations to solve C and D. So you see the velocity, I have to differentiate it. You see here, I have to differentiate and then put the velocity, the initial velocity, and then I can solve one of the constants. And then if I put the displacement in the original equation, I can solve for one constant. So if we do the solution, you can get C here as 0.5 and D here is 0.8 divided by omega n. So the equation will look like this. And then if I plot this equation for a certain value of omega n, this will look like this. You see, this is actually a sinusoidal wave. So if I displace the structure, if I displace my KL tower and then let go, it will vibrate with a sinusoidal motion. And then this will continue for the rest of the life, rest of the time, because there is no damping. So it will not come back to its equilibrium position. So what are the components of this plot? You see, I have displaced it. You see the U0, the initial displacement. And the velocity is nothing but the slope of the displacement versus time curve. So in this particular example, I gave the KL tower a displacement of 0.5 meter and then a velocity of 0.8 meter per second. So this will vibrate like this. And then the amplitude can be calculated. E can be calculated from C square plus C square. Here we have our C, 0.5, our D, 0.8 over omega n. So if you put it here for a certain value of omega n, you can get the value of the amplitude. And of course, the period is from same phase to same phase. So it can be from, let's say, from this point to this point, or it can be from any same phase to same phase point. That will give me the period of vibration. All right. Now let's solve the equation for damped free vibration. So when we talk about damped free vibration, you see the C term will be there, but since it is free vibration, the right-hand side will be 0. There will be no P. Again, this is a second order homogeneous ordinary differential equation. So we can use the same form of assumed solution for the equation. Like this, U equals to A e to the power lambda T. And then again, if I differentiate it once to get U dot, differentiate it again to get U double dot, and substitute in the original equation, I'll have a big equation. And then if I set one of the term not equals to 0, then the auxiliary equation will be this. Now, what kind of equation is this? This is a, what kind of equation? This is a quadratic equation, right? So the solution of quadratic equation, you already know, ax squared plus bx plus c equals to 0. The solution of x is what? Minus b plus minus square root of b squared minus 4ac divided by 2a, right? So that's the same equation we apply to get the solution for lambda. Again, you can see here there will be two solutions for lambda because there is one plus, one minus here. So that's why there will be one lambda 1, there will be one lambda 2. Right? Now this is very interesting. So can I show my face for a while and then show you what's going to happen? Yeah. Okay, I need something. Yep. Okay, can you see me?
Yes.
Yes.
Very good example.
Yes.
Okay. Okay, so you can see here in the equation, you can see there is a term inside the square root. Now, this is mathematics and this is engineering. You know, what is engineering? Application of pure science. So you see, we will see now how the structure will vibrate depending on the term inside the square root here. If the term inside the square root is positive, okay, it's positive, then if I displace my KL tower, it will come back to its equilibrium position without any oscillation. So you see, I pull it here and then let go, it will just come back to its equilibrium position. It's not going to oscillate. And again, if the term inside the square root is equals to 0, the same thing will happen. So what is the difference between 0 and positive values? Now, when it is 0, if I displace the structure, let's say the structure has a damping in such an amount that the term inside the square root is 0. So if I displace it and then let go, it will come back to its equilibrium position without any oscillation at the lowest possible time. So if it is 0, the term inside is 0. Then if I displace it, it will come back to its equilibrium position. Let's say 2 seconds. it will come back here at 2 seconds without any oscillation. So now if the term inside the square root is, let's say, +2, then again, it will come back to its equilibrium position, but it will take longer time. Let's say 3 seconds. And then again, if the term inside the square root is 10, okay, overdamped. So it will come back to equilibrium position, but it will be even slower. It will take even longer time, let's say 20 seconds to come back to its equilibrium position. So that is 0 and positive value. And then if the term inside the square root is negative, then we call it underdamped. So underdamped means if I displace my structure and then let go, it will oscillate. It will oscillate, and then after some time, it will come back to its equilibrium position. Right? Do you get my point?
Yes, good.
Yes, sir.
Okay, that's good. All right, let me go to my slides. Now, can anyone tell me all the structures that we see around us, are they critically damped, overdamped, or underdamped? Can anyone tell me?
Underdamped.
Yes, that is very true. So that means that if we displace any of the structure, let's say KL Tower, let's say the Petronas Twin Tower, or any other building, if I displace it from its equilibrium position for somehow with a very high power of crane and then let go, it will actually oscillate and then it will come back to its equilibrium position after some time, right? So we have overdamped, we have critically damped, and then we have the underdamped system. Since most of our structures are underdamped, we'll try to solve the equation for the underdamped situation. That is, the term inside the square root is negative, meaning that our C square is smaller than 4mk. Okay. So if I use that, if my C square is smaller than 4mk, then this term will be negative, right? So the minus sign will come out with the square root. That means there will be J coming out. And then if we do some mathematical changes here, finally, both lambda 1 and lambda 2 will look something like this. Now, I told you before that it is very difficult to get the actual damping of a system because it depends on the internal friction of all the materials that the structure is made of. That's why we never use the term damping in our structural dynamics. The term that we use is damping ratio. Okay, the term you use is damping ratio. Now, what is damping ratio? Damping ratio is how much the structure is damped if you compare it with the critical damping. Okay, do you understand? So, for example, let's say I'm talking about my KL tower. So, what is the ratio between the actual damping of the KL tower and its critical damping? Now, what is the critical damping? I told you that critical damp situation is the term inside the square root equals to 0. That means C square equals to 4mk. So C square equals to 4mk will give me the critical damping. Since this will give me the critical damping, that's why I put a subscript CR in C. So that is the critical damping. So if I square root it, I'll get the critical damping. The equation will be something like this. And then after some modification, the critical damping is given by 2m omega n, or 2m square root of k over m. So you see, it depends on the mass of the system. It depends on the stiffness of the system. Or otherwise, it depends on the mass and frequency of the system. So if you know the mass and the stiffness of the system, you will know what is the critical damping of the system. And then the damping ratio is nothing but C over CCR. The actual damping, which I don't know, divided by CCR. So let's say, for example, KL tower, the actual damping is 5 units. And then the critical damping is 10 units. So what is the damping ratio? 5 over 10, that is 0.5, right? So that's what the damping ratio gamma means. Sometimes it will be used as gamma, and in some textbook you can find the symbol chi to represent the damping ratio. Okay, so that is my damping ratio. So let's say, okay, let's go and then modify our equation. So I told you before that the lambda 1 and lambda 2 are given by these two equations. So if I substitute in my original solution, which is this, e to the power lambda 1t, e to the power lambda 2t. If I put lambda 1 and lambda 2 in the equation, it will look like this. And then I can take out the common term, you say e to the power this, e to the power this, that can be taken out. And then inside there is another term here. And then this term can be changed. Don't focus too much on the equations. Just look at the final equation. So this can be also the j theta minus j theta can also be converted into trigonometric terms. So if I do that, if I take the common terms, finally, this is my equation of motion. You can see here, there's an exponential term here, and then there's a sum of sine and cosine here. If you look at the sine and cosine terms here, it's similar to that one of undamped free vibration. Now you see there are so many things here, so many things here. So let us try to simplify this. Okay, let's try to simplify this with whatever we have just now derived in terms of damping ratio. So you see the critical damping is given by this equation, and the damping ratio is given by the ratio of C over CCR. So if I put the CCR equation here, I can now say my C, my damping of the system is nothing but 2m omega n times gamma. And since in the equation you have already seen there is what? C over 2m. So I just try to find what is C over 2m. C over 2m is nothing but gamma omega n. So I just bring this 2m in the denominator to the left-hand side. So it will bring me C over 2m equals to gamma omega n. All right. Now let us try to substitute all this in the equation. You see, there's a C over 2m here. There's a C over 2m here. There's a C over 2m here. All these three can be replaced by gamma omega n, right? And then K over m. K over m is what? Omega n square. There's the frequency square. Okay? So if I change this term inside the square root, it will look something like this. K over m will be square, omega n square. And C over 2m is gamma omega n. So this square. So if I simplify it, it will be omega n multiplied by a term that is corresponding to the damping ratio. Now this product, the natural frequency multiplied by the term 1 minus damping ratio square root is known as the damped natural frequency. Again, I'm turning on my camera to show you something. Yeah. So undamped, that is an ideal situation that doesn't exist in nature. There is nothing as undamped. So the undamped frequency, the structure will vibrate. Okay, if I displace it, it will vibrate with a certain frequency. Damped frequency, it will also vibrate with a certain frequency. But you can see here, if you look at the equation of the damped and undamped, the difference is this term. 1 minus. So you see the omega d, the damped natural frequency, will be a little bit smaller than the original undamped natural frequency. Now, can anyone tell me what is the usual value of damping ratio in civil engineering structures? Can anyone, does anyone have any idea how much will be the damping ratio? How much is the actual damping of the system if you compare it with the critical damping of the system? Now, maybe you don't have an idea. Usually for concrete and steel buildings, the damping ratio varies from 2% to 5%. That is, the value of gamma is either 0.02 to 0.05. Okay, do you understand? So it's very small if you compare to the critical damping. 2% to 5%. That is the damping ratio of real structures. So if you see here, if it is 2%, it will be 1 minus 0.02 square. So it's almost omega d and omega n will be equal, right? So if I change all these things, the complicated equation, then the equation of the solution will be something like this. Now you see here, in this equation, there is two terms. There are two terms. One is this exponentially decaying term, and then the second term is a harmonic term. So if I plot it, then it will look something like this. Because of the because of the exponentially decaying function, it will try to decay, and then because of the harmonic part, it will try to oscillate. So if you combine these two, it will be a harmonic function that will decay to 0 after some time. Meaning that, again, I'm turning on my camera, meaning that if you displace your structure from the equilibrium position and then let go, what will happen? It will vibrate, and then it will come back to its equilibrium position after some time. Okay, depending on how much damping the structure has. If the structure has a very high damping, then it may happen like this, very fast. If the structure has a very low damping, then it may oscillate for a longer time and then eventually come back to its equilibrium position or the zero position. All right. Okay, so these are the same things: the initial displacement, initial velocity, and of course the amplitude. Again, I didn't see you, so show you this equation in terms of sine and cosine can also be converted. This part, the second part, can be converted to one single sine wave with a phase angle theta. The same thing. In this case also, E will be nothing but square root of A squared plus B squared, and then theta will be the phase angle. All right. Okay, so here is the plot that I showed you just now with my video on. So if I displace my structure with 500% damping and then let go, you see it will come back to its equilibrium position with longer time. And then this is my critical damping, 100%, or the damping ratio 1. So it will come back to its equilibrium position without any oscillation with the minimum possible time. You can see here, almost like 7 seconds, it will come back to 0. But this one is 500%, so over damped. It will take very long time, maybe 30 seconds, 35 seconds, and so on. And then if it has a lower damping ratio, 5%, which is less than 100%, so that will oscillate like this. Okay, so most of our civil engineering structures are actually oscillating like this. Now, if I have this kind of plot, can I find the damping, the actual damping? Now that is interesting. Again, I'm turning on my camera for 1 minute. I'll be going very fast because our timing is running fast. So if I can displace, now you see, very interesting. If I can somehow displace my KL tower and then let go, I'll have this plot, right? So this kind of plot I'll have, the plot I'm showing you just now. So from this plot, can I get the frequency and the damping ratio? Yes, of course we can, because you see from here to here, if I can get the T, I can measure the T here. So T is nothing but 1 over F. So I can get the frequency. Now, let me show you how can we find the damping ratio. Okay. So you see here, this is the equation of the solution of the damped free vibration system, right? This is the equation. And then in this equation, which part is showing you the amplitude? Yes.
Sorry, Prof, can I ask
anyone
questions?
Yes, you can.
So in some cases, can the damping increases over the time? For example, due to environmental changes or etc.
Yeah, it may, if there is some, not because of environmental changes, but if there is some change in the composition of the structure. So there may be some problem with the internal friction between the materials. Then obviously it may change. Yes.
Oh, okay. All right. Thank you.
Okay. Yeah, that's why there is now a very new direction in civil engineering, that is a structural health monitoring. So we will put some sensors in some sensitive structures and then monitor the dynamic behavior, static behavior over a long time. So we can monitor how much is the damping, how much is the frequency of the structure. Then eventually we can actually take care of the structure, right? Now you see, this is a sinusoidal curve equation. So what is the amplitude on this equation? Anything that is with the sine, you see? So here, the amplitude is given by this capital E times the exponential term. So this will give me the amplitude, right? So you see the amplitude of the nth peak. Let's say, for example, this is my nth peak, n, okay? And then the time from 0 to here is t seconds, okay? From here to this peak is t seconds. So what will be the amplitude in this case? You see, e to the power gamma omega n t, okay, at t seconds. So what will be the amplitude of the next peak? This peak. What is the time here? You see, the time from 0 to this peak, the first peak is t, right? From here to this t. And then from this peak to this peak, the second peak, That is the period, capital T. So the time corresponding to the second peak will be small t plus the capital T. Therefore, you see the amplitude of the next peak will be given by only the time here changes, t plus capital T. Now, if I take natural log on both sides of this equation and both sides of this equation, and then divide the first equation with the second equation, I'll get an equation like this. Natural log of un over un plus 1 equals to this. And you also know that natural log of e to the power something is that something. So if I say natural log of e to the power a, it will be a. That's why it is like this. And then natural log of e to the power b is b. This is the third. So if I simplify, you can see here is gamma omega n t, and we know my t is 1 over f, and 1 over f is nothing but 2 pi over omega d, the damped natural frequency. Okay, so if I again simplify this equation, it will become like this. And then you already know that omega n and omega d are very close to each other. That's why I can say this ratio is 1. So you see, from this equation, I can find my gamma if I take the 2 pi to the left-hand side. So you see, the damping ratio is nothing but 1 over 2 pi natural log of the nth peak divided by the next peak. Meaning, if I can measure this peak and this peak somehow with a ruler or from the scale, then I divide this peak by this peak, like this, n over n, take the natural log, divide by 2 pi, I'll get the damping ratio. So you see, that is the beauty of that particular curve. So if you have this kind of plot, you can get the natural frequency, or the damped frequency, and also the damping ratio of my structure. Do I have enough time to go through the examples, or later I can share it? Dr. Yasmin, do you allow me another 10 minutes?
Yeah, sure. Take your time. Yes,
Okay.
you can.
Okay,
Sure,
great.
definitely.
Okay,
This good
thank you.
example is good for their upcoming exams.
Yes, sure. Okay. All right. So I'm going to show
They're
you a
going
few
to have
examples
the
here.
exam next week.
Oh, okay. All right. Okay. So you can see here, there are a few examples here. So this is the spring mass damper system. So here, the question is, a mass of 100 gram is supported by a spring stiffness of this K value. Estimate the natural frequency. So this question is showing you something like, let me turn on my camera first. Yeah. So I am hanging something. I'm hanging something by a spring. So the spring is fixed here. So I'm hanging a mass of a certain grams, 100 grams. And then this spring has a stiffness of 90 Newton per millimeter. So what is the frequency? So you already know that the frequency equation is omega n equals to square root of k over m. Now, if I want to substitute the value of k and m in this equation, I have to convert into the basic unit. So therefore, m must be in kilograms, and then k must be in Newton per meter. Please remember that very carefully, all right? So you have to convert the equations, convert the units into the basic units. So k has to be in Newton per meter, and then m has to be in kilograms. So if I convert them and then substitute here, you see the frequency is 948.7 radian per second. So from radian per second, if you want to go to it in the hertz, you have to divide it by 2 pi. So if I do that, I'll get 151 hertz, meaning the mass with the spring system will vibrate 151 times in 1 second. You cannot see it by your naked eyes. You have to have a very high-speed camera to see the vibration. Okay, so let us continue the same problem. If the system in question 1 is given an initial displacement of 5 millimeter and then released, derive an equation to describe the subsequent motion. So there are two conditions. One, assuming there is no damping, and then the second one, assume there is 1% damping. Means that I displace my spring. Again, so there is this mass suspended by a spring. So I displace it by 5 millimeter, either to the bottom or to the top, doesn't matter. So I displace it and then let go. So what happens? It will vibrate, right? So what is the equation? So what is the equation that will describe these vibrations? Right, that's what we have to find. So you see, the first condition is no damping, that is undamped free vibration, right? So the solution of undamped free vibration is this. So if you can find out omega n, if you can find out C, if you can find out D, we put everything in the equation, that will show me the equation to describe this, right? So we already have omega n from the previous solution, which is 948.7 radian per second. So we already know omega n. Now to find C and D, we have to substitute the two initial conditions. We need two initial conditions, okay? We cannot just use one. So here I mentioned that the initial displacement was 5 mn. That means the displacement at t equals to 0 was 5 millimeter. Again, you have to convert it into meter. Since I didn't mention anything about the velocity, that means the velocity at t equals to 0 was 0 meter per second. It should be 0 meter per second, not meter, right? So how can I get C and D by substituting these two values? So I can substitute U at 0.005 in this equation. If I put t equals to 0, t equals to 0, so it will give me C equals to this value. And then to substitute the velocity term, I have to differentiate this equation. The differentiation is very simple. Cosine will become sine. You see negative sign with omega n coming out. Sine will become cosine with omega n coming out. So that's the differentiation. And then I can substitute at t equals to 0. So all the t's will be 0. And then the value of u dot 0 is 0. You see the right-hand side? Left-hand side is 0. So if I do the calculation, our d will be 0. So C has a value of 0.005. I put it here. D is 0. So I get the equation. So this equation will actually give me the equation of the vibration. So it will vibrate. It's undamped, so the vibration will go on forever. Okay, so that is the solution of the first part. How about the second part? Assuming a damping of 1%. So it is damped free vibration. So what is the equation of damped free vibration? This is the equation of damped free vibration. So here you see there is omega D, and omega D is nothing but omega n multiplied by square root of 1 minus gamma square. And gamma is given as 1%, that is 0.01. Right? So you see it's almost equal, 948.7, 948.65. If I just take 4 significant figures, it will be same, right? Okay, so I can substitute the two initial conditions. U at 0 is this, U dot 0 as 0 in this equation. So I can straight away put it, so I get B here, the initial displacement. To substitute the velocity, I have to differentiate this equation. Is it difficult to differentiate? No, it's a product of two functions. So the differentiation will be you keep one function, differentiate the other, and then you keep the second function differentiate the first part. So that is my differentiation of this equation. And then you put t equals to 0, 0, 0, 0, and then u dot 0, which is actually 0. And then after doing some calculations, you'll get my A value is this. So I have my A value, I have my B value, I have my gamma, I have my omega n and omega d. So if I put it here, that will be my equation, giving me the solution of the second part of the problem. Okay, so that is the spring mass system. The next question, there's another part. How long will it take for the amplitude of vibration to be reduced to 2 millimeter? Again, I'm turning on the camera to explain you what am I asking for. So you see, I have displaced my spring by 5 millimeter, right? And then let go. So it's vibrating. After how many seconds or what time it will become 2 millimeter? So I displace it by 5 millimeter. After how long it will be 2 millimeter? That's the question. That's the next question. Okay. So you can see here the equation of motion. Sorry, the solution of the equation is this, which can also be written in terms of this because I'm talking about amplitude. So which part of this is amplitude? This part only, right? This times E is giving me the amplitude without the sign. Now what will be E value? E is nothing but square root of A square plus B square. And in the previous problem, I already have my A, I already have my B. So I can calculate the value of E, which is this. So which part is amplitude now? This part is the amplitude. So this amplitude will become 0.002 meter or 2 millimeter. So if I just equate this and then solve for t from this equation, I can find this 0.0097 seconds. Of course, the time is very fast. Why? Because the spring is very strong spring. So it will move very fast and then come back to 2 millimeter. It's less than 0.1 seconds. Okay, the next problem is a portal frame. There are two columns, and then there's one beam connected by the two columns. The portal frame in figure 1 can be considered behave as a single degree of freedom system. You see, if I consider the two columns as one single column, and then I somehow lump all the mass in one point, this will also look like a KL tower, right? So one column and then supporting all the masses. So it will can be this one can also be idealized by a single degree of freedom system. So the mass is given. If you look here, the mass is given here, 5,000 kilograms. E value and I value is given. What is E and I? E is the material property or Young's modulus. I is the cross-sectional property or moment of inertia or second moment of area, right, of the column section. It depends on how you make your cross-section of the column. Now I have to find the value of K and M to find the omega n, the natural frequency. The mass M is given, 5,000 kilograms. How about the stiffness K? This is not a single column. This is not a spring, okay? This is a flexural system. So this flexural system, there are two columns, and then the bottom end is fixed. The top end is rigidly connected to the beam. So in this kind of situations, the stiffness of a single column is given by this equation, 12 EI over L cube, where E is the moment of inertia, E is the Young's modulus of the material, which is given. I is the moment of inertia of the cross-section, which is also given. And then L is the length of the column, which is also given. Now, since there are two columns, you have to multiply this with 2 to get the total stiffness of the two columns. So if I substitute here, I can get the total stiffness of the two columns. So I know the stiffness if I convert it into single column, and then I know the mass. So if I put it here, I'll get the frequency in radian per second. And then if I divide it by 2 pi, I'll get in hertz. All right. Last example. So an experiment has been performed to determine the damping ratio. So what has been done? This portal frame was displaced by a crane and then let go. Then when it was let go, some plot like this was obtained, okay? And then it was seen that measurement of successive peaks of the transverse vibration were 150 millimeter and 145 millimeter. So that means UN is 150, and then the next peak, since it is reducing, was 145. So what is the damping ratio? So we already have the equation of damping ratio like this, 1 over 2 pi multiplied by natural log of UN over UN plus 1. So I just substitute here. It doesn't matter what unit you put it here because it will be divided. So the units will be cancelled. You can find it will be 0.005, meaning 0.5% of damping. Usually, if you are asked to find out the damping of the system, you put it damping ratio, you put it in terms of percentage. That's easier to understand. Okay, so that's the end of my lecture today. I'm going to share these slides with Dr. Yasmin, so that if you have, you can actually go through this, and then if you have any questions, you may ask me later. Okay, back to Dr. Yasmin. Thank you very much for listening.
Okay, all right. Thank you so much, Associate Professor Dr. Mohammed Parvez Anwar. Now I would like to open to question session. Does anybody have any question that you would like to ask? Dr. Raizam? Dr. Nabaya? How about the students?
Either they understood everything or didn't understand anything.
Yes, what you thought, partly mostly is what we are learning in class.
Okay.
I guess it's the morning. Okay.
It's the morning of Saturday, yes.
Yes, it's the morning and Saturday. Uh, when we measure damping in the system, what kind of challenges can be associated during the measurement? What are the challenges in the
Okay.
calculation?
What happens? Yeah. In dynamic analysis, we usually don't measure the damping of a system. We actually there's a certain value of reinforced concrete structure. There's a certain value of steel structure that has been actually found out by many scientists by different experiments. So we just use a value for the concrete structure. Usually we use 2 to 3%, and then for steel structures we use a bit higher value, maybe 3 to 5%. But if you really want to get the damping ratio of a system, then you have to do the actual test. So you have to displace the structure by a heavy crane and then let go, and then got this plot, and then you can get it. This method is actually done for small bridges. So small bridges, they will pull down the bridge by a crane and then let go with sensors, and then they will obtain the plots by some sensors like maybe strain gauges or accelerometers. Then you can get the actual damping of the system. So the measurement requires a very heavy machineries to actual calculation.
Okay. All right. Any other questions?
Okay, Prof.
Yes.
Can I ask, Prof? Okay, normally in practical systems, where is the line drawn between underdamping and overdamping, and then maybe what informed the decisions?
No, actually, overdamped and critically damped are ideal situation. There is no structure that will be overdamped ever. That's the nature. In the nature, you can never find any system that is overdamped. All the system is actually underdamped. And if you look at the percentage, it's 2% to 5%. So it's actually very heavily underdamped. No way the actual damping of the structure will go near the critical damping. That's nature. It's created like that.
Okay, Bro. All right. Thank you, Bro.
Okay.
Okay. Any more other questions? Okay. All right. So, on behalf of everyone here, I would like to extend our heartfelt gratitude to Associate Professor Mohammed Parvez Anwar for his insightful talk on the vibration engineering. So, his expertise and knowledge is valuable for our civil engineering students, and we hope this crucial field will be appreciated more by our students. So your discussion on vibration and the structural performance that you explained just now not only has broadened our perspective, but also has highlighted the real world application, yes, in engineering that we must consider. So we truly appreciate the time and effort and the dedication of your sharing knowledge with us. So we again would like to thank once again for everyone for participating, and thank you again for Dr. Parvez for your enlightful session. Okay, so thank you. Let's make a clap, and we hope everyone
Thank you very much.
we want to take a picture. Can everyone open the camera, and at the same time, don't forget to fill in your attendance in your future. Okay, so can everyone open the camera? Okay, I know your room is a mess. Yes, I.
Thank you very much. It was a
Okay.
pleasure. It was a pleasure to be a part of this. Thank you. Thank you very much.
Okay.
Thank you.
Okay. Okay, I'm gonna take a picture. Okay, one Ahmad. Okay, there you go. All right. Okay, one. Okay, hold on. 1, 2, 3, smile. Okay. All right. So got one photo already. Wait. Maybe you can switch off your screen. Is that okay? So that I can get everyone on the camera. Hold on, hold on. Okay, let me take one more time. How to make the screen bigger? Dr. Parvez, can you stop sharing?
Okay, sure. All right.
Okay, now I can get more photos. I see. All right. Okay, one big smile. 1, 2, 3. Okay. All right. Okay, there we go. Okay. All right. Thank you, everyone, and have a nice weekend. Thank you, Dr.
Thank you.
Parvez.
Have a nice weekend. Take care, everybody. Thank you. Thank you very
Thank
much.
you,
Yes.
Dr.
Thank
Pervez.
you,
We
Doctor.
value your
Thank you.
presentations today.
Check it
Thank
out.
you.
Okay. Okay, thank you, everyone.
Thank you, Dr. Yasmin. Thank you.
Okay, all right. Thank you. Have a nice weekend semua.
Okay.
Okay, Assalamualaikum.